Alright, welcome to lecture 2 of our real analysis video series. You're on the Argmin YouTube channel, I think, maybe. In this lecture, we're going to be talking about how we're constructing the reals. Last lecture, we introduced decimal expansions, and maybe I wasn't clear on how they're going to be used. We're going to be using them to construct the real numbers, and we'll see how we do that coming up. So, first off, our goal is to construct. Let me check my microphone is on. Okay, it is. Construct R via decimal expansions. For example, 0.729 repeating is equal to 0.73. We can't directly use decimal expansions yet because we have duplicates like this. Let me move that off so that the note looks cleaner. Can't directly use decimal expansions because of duplicates. Three, we defined what it means for f to be in an equivalent to another decimal expansion g. So f, when it has this repeating structure of 9s at the end, and g when it's the same number in the reals but it's a different decimal expansion. So we said, f is similar to g if this or f equals g. Let's go on to constructing the reals. So if you haven't seen them before, tilde is an equivalence relation. That just pretty much means they're pretty much the same, or you can treat them the same. So let X be the set of decimal expansions let R be the set of equivalence classes of X under tilde. So that's it, that's the reals. So for example, 0.729, as we said before, this member of the equivalence classes of X under tilde is written like this with the square brackets, and the corresponding set of everything that's equal to that are 0.729 itself and 0.73. I just realized I wrote something wrong. So this is supposed to be AK plus 1. So it's that AK, but you add 1 to A sub K. All right. So these are all in R. So by convention, we avoid repeated 9s. For example, we'll write 0.73 instead of this this equivalence class notation. So when we write 0.73, it just means either one of these. Now going on to visualize R as a real number line, we have two problems. So in the last lecture, we said we always have orderability, so let's call that property A. And the second property was it was complete, meaning there were no gaps. So we've been using real numbers for a while, up to now, and now we're going to show that this construction has the properties that we're used to. So this orderability and completeness, these properties. So first off, let's look at problem A. So we know that we can compare integers. So if we start off from this, it's not covered in this class, but you can look at piano arithmetic for that. Now we're going to show the ordering for rational numbers. And from there, we're going to show the ordering for the reals. So take two rational numbers a over b and c over d in the positive rational numbers, or non-negative, I mean, where, that's not how you spell where a, b, c, and d are greater than or equal to 0, and b and d are not 0. We define the ordering for the rational numbers as a over b is less than c over d if and only if AD is less than CB. So we multiplied both sides by BD. Now let's look at it for the negative rationals. Let Q1, Q2 be in the negative rationals. Define Q1 less than Q2 if and only if negative Q1 less than Q2. So we have, we just used this definition to get this definition, So this will be positive and this will be positive. Oops, I'm missing an, or I didn't write the negative there. So that gives us orderability for all of the rational numbers. Unless we have a case where one's positive and one's negative. So if Q1 is greater than 0 and Q2 is greater than 0, is less than 0, we say Q1 greater than Q2. All right, let's first define x in, define something. So let x be a real number. And let's look at the non-negative case for now, and y be another one. We say x less than y if there exists n greater than or equal to 0 such that ai is equal to bi for I less than n and a n less than b of n. So we're saying eventually one of the numbers in the decimal expansion is greater than the other. So let's look at an example. X is equal to 27.32684 and y is equal to 27.32691. So scanning along, we see everything is equal up to this third part. Oops, I won't even try. So we have 27.326 here and 27.326 here. But here we have the 8, which is less than this 9 at the next spot, giving us the n equals, so that's this is going to be, this is the 0, this is the 1, this is the 2, this is the 3, this is the 4. So n equals 4. So a 0 is, let's confirm it, b0. So that's because 27 is equal to 27. A1 is equal to b1 because 3 is equal to 3, and so on. And finally, and that's for all I less than n, a n is less than b of n, because 8 less than 9. And we can extend this to all of the real numbers, so we defined it for the only positive ones, or non-negative ones, sorry. Using the same method as Q to all as rational numbers. Whoops, Q less than 0. So as an exercise, let's just do that. So if A, B are in R less than 0, then A is less than B if and only if A, negative A is greater than negative B. And we know how to know how when one is greater than the other, because here A is going to be positive now and B is going to be positive, so we have that ordering defined from before. And if one is positive and one is negative, 0, B less than 0, A is going to be greater than B. proposition. This is known as the Archimedean property. If x, y are non-negative, then there exists n in the natural numbers such that nx is greater than y. So a proof: consider the number y over x that is non-negative, since there is no largest natural number there exists n such that n is greater than y over x. This implies nx greater than y, thus completing our proof. So now let's go on to the second property we wanted of completeness, proposition. Take an x in R and let epsilon greater than 0. There exists a q in the rational numbers such that the absolute value of x minus q is less than epsilon. So what this is saying is there's no gap in the real line, because you can always have a rational that can be jammed in there. So proof: let epsilon greater than 0 be given. Say x is equal to a naught, continuing from there, and take a k as a rational, I'm mixing up my words. K as a natural number such that 10 to the negative k is less than epsilon. And then let q be a rational number, being the first k, or the first k plus 1 digits of x. Oops, pen tool. So this is rational because it's a finite number of digits that are non-zero. Then we have x, let's keep the proposition in view, minus q is equal to 0, 0 repeating, all the way up to ak plus 1, and so forth. It's equal to 0.00, whoa, ak plus 1, so forth, because we took this is an absolute value, and this is going to be less than this number, where it's k plus 1 zeros. And that number is equal to 10 to the negative k. I guess there are 1. 10 to negative 1 would have just 1 0, so there would be k 0, sorry. And we chose this number, 10 to the negative k, so it's less than epsilon, thus completing the proof. So we've now, whoa, oh, that's not what I wanted. Highlighter. We've now shown this property from this chain of equalities and inequalities. All right, that completes our construction of the reals. Now let's move on to something called least upper bounds. So let's go over a couple of terms first. A set X is a subset of R is bounded above if there exists a real M such that X is less than or equal to M for all X in X. We call M an upper bound for X. So that's what we were defining. Now let's do bounding from below. A set Y is a subset of R is bounded below if there exists M in R such that M less than or equal to Y for all Y in the set Y. So this number is less than anything in the set, less than or equal to. We call M a lower bound for Y. A set is said to be bounded if it is both bounded above and below. So there's a lot of terms here: bounded above, bounded below, upper bounds and lower bounds, and finally bounded. Now, suppose some X subset of R that is non-empty is bounded above an upper bound. L is a least upper bound for X if whenever M is an upper bound for x, L is less than or equal to M. This is also known as a supremum. And the notation for this is L is equal to the supremum of x. And similarly, there's something called a greatest lower bound. Or infimum. Of x. Let's just write out its definition. Suppose, let's call it y this time, subset of R bounded below an upper bound, a lower bound. L is a greatest lower bound for y if whenever M is a lower bound for y, we have that L is greater than or equal to M. And also, this is known as the infimum. The notation uses the word inf for these, but I think it's more evocative to think of it using the other word, greatest lower bound. So it's a lower bound and it's the greatest one. Similarly for the supremum, it's also known as the least upper bound. It's an upper bound, but it's the smallest or the least one. That's less than other upper bounds. Okay, that's it for this video.